Imagine you're in medical school. For 2 years, you just study anatomy, including thousands of pictures of healthy brains, sick brains, young and old. You build a mental map. Because you have that foundation, if I show you a rare genetic mutation you've never seen, I only have to show you once. You compare it to your mental map, spot the anomaly, and learn it. Humans are efficient learners. But until recently, medical AI didn't work like that. To find a tumor, you had to show it 10,000 tumors. To predict a stroke, start over with another 10,000 examples. Power, but no specialization. That just changed. A new study in Nature Neuroscience unveiled BrainIAC, a foundation model that finally sends AI to brain-specific medical school. Today, in Cortex and Code, we're exploring how BrainIAC learns, why it bridges biological and silicon intelligence, and what it reveals about intelligence itself. The foundation. How do you teach a computer to understand a brain without telling it what to look for? Self-supervised learning. Think of a baby learning about a block. The baby rotates it, sees it in a different light. Its brain learns that despite different angles, it's the same object. BrainIAC did this at scale. 48,965 brain MRI scans that involve Alzheimer's, stroke, autism, healthy controls. Using contrastive learning, the AI plays a game. It takes a scan, distorts it, and learns that this rotated hippocampus is still the same hippocampus, but a hippocampus versus a tumor should look different. After millions of iterations, it learns the brain's fundamental geometry, white matter, cortex, what normal looks like, without a human labeling a single pixel. It's building a brain-specific mental map, folds, fissures, fibers. Why now? 3 things converged. 1. Large-scale datasets. Researchers aggregated 48,965 scans from 34 different sources, including ABCD, ADNI, and Oasis 3. 2. Handware advances made training on full 3D brain volumes feasible. 3. Self-supervised techniques like contrastive learning proved they work on medical images. BrainIAC is what happens when neuroscience, big data, and AI architecture align. Part 2. Few-shot learning. Here's where psychology gets interesting. In cognitive science, schema theory explains how chess masters don't memorize positions. They recognize patterns. They learn the grammar of chess, so they parse rare positions instantly. BrainIAC works the same way. Traditional AI needs big data, but in medicine, especially rare diseases, we have small data. Because BrainIAC has that pre-learned mental map, it mastered few-shot learning. Think of BrainIAC as a veteran club bouncer. He's seen a million faces. Hand him a blurry photo of one troublemaker, a rare genetic mutation, he spots them immediately. In the study, BrainIAC identified genetic mutations in brain tumors with just 1 example per mutation type. It outperformed models trained on 10 times more labeled data because it understood anatomy, not just memorized patterns. That's not human level. We learn from true one-shots, but for AI, massive leap. Part 3, where AI thinks like a neurologist. BrainIAC just aced 7 different diagnostic tests, but here's the mind-blowing part. It didn't just guess, it thinks like a neurologist. For years, AI in medicine has been a total black box. Great results, but no clue how it got there. Total trust killer. To fix this, researchers slapped on Saliency Maps, basically heat vision for the AI, showing exactly what part of the brain it's staring at. The big reveal was incredible. When predicting mild cognitive impairment, that sneaky first step to dementia, BrainIAC zeroed in on one spot, the hippocampus. If you know your brain, that's the established memory HQ. It wasn't looking at static or noise, it was studying the exact biological structures a human doctor would check. But wait, there's more. BrainIAC is now moonlighting in brain age prediction. Forget your birthday, your chronological age. The real story is your biological age, how fast your cells are wearing out. BrainIAC looks at an MRI and spits out your brain's visual age. Imagine you're 50, but your brain looks 60. That 10-year gap is a terrifyingly accurate biomarker for accelerated aging and higher dementia risk. The best part? Saliency maps mean doctors can actually trust this thing. They can see the AI is spotting genuine damage and atrophy, not just some random numbers game. Conclusion: the universal resident. Why does this matter? Medical data is messy. Boston hospital scans are not the same as rural Montana clinic scans, different machines and settings and noise. However, BrainIAC is robust as it ignores static and focuses on anatomy, signal, not noise. Real-world impact? A Montana radiologist gets a second opinion trained on 50,000 brains, catching rare mutations they'd see once in a career. Researchers test Alzheimer's drugs faster, using brain age acceleration as an early signal, not waiting 5 years for symptoms. ER doctors get instant triage, migraine or stroke needing immediate surgery. We're moving from narrow AI, one trick, to generalist AI, understanding the human body's context. It's not replacing the doctor, it's giving them a resident, the one that's seen everything, never tires, and explains its reasoning. And maybe it's showing us that intelligence, biological or artificial, follows the same rules. Learn the foundation, recognize patterns, focus on what matters. Thanks for watching. If you like the video, don't forget to click the like and subscribe button. See you next time.